If you've been following the intersection of AI and robotics, you know that the holy grail right now is the Vision Language Action Model, or VLA. We already have these incredibly powerful vision language models, like GPT-4V, Claude, or Qwen, that have essentially compressed the internet's visual and semantic knowledge into their weights. The dream is simple. Plug one of these models, feed it a camera feed and a prompt, and have it output motor commands for a robot. But there's a fundamental architectural friction here. Transformers are natively discrete. They predict probability distributions over a fixed vocabulary of tokens. Robot actions, on the other hand, are continuous. They live in the realm of real numbers, joint angles, torques, spatial coordinates. How do we bridge this gap? Well, historically, the robotics community has treated this like a plumbing problem, and they've built some pretty complex pipes. The first popular approach, used by models like RT2 and OpenVLA, is discretization. You chop the continuous action space into, say, 1,000 distinct bins, and you force these into the VLM's vocabulary. But think about what this does to the latent space. You are either hijacking existing word tokens, forcing the model to forget what the word apple means so it can mean move 2 centimeters left, or you are adding completely new tokens whose embeddings have to be learned from scratch, throwing away the rich, pre-trained language priors. The second approach is to bolt on a completely new neural network at the end, a generative action head. Models like Pi-0 take the hidden states of the transformer and feed them into a diffusion or flow matching model to output continuous actions. This works beautifully for fine-grained control, but it's heavy. You're introducing millions of new parameters that need to be aligned and fine-tuned, often degrading the underlying VLM's raw reasoning capabilities. What if there was a way to get the best of both worlds? What if we could achieve state-of-the-art robotic control with zero modifications to the architecture or the vocabulary? Enter a 2025 paper from NVIDIA researchers titled VLA-0, Building State-of-the-Art VLAs with Zero Modification. Their solution is delightfully, almost absurdly simple. Just ask the model to type out the numbers. Instead of custom tokens or diffusion heads, VLA-0 takes a standard, off-the-shelf vision language model, specifically Qwen VL 2.5, and prompts it to output actions as raw text strings. If the robot needs to move to coordinate 0.512, the model auto-regressively generates the string 5, 1, 2. Geometrically, they simply normalize the continuous action space to a fixed integer range 0 to 1,000. The VLM just outputs these integers, separated by spaces. Now, if you're a computer scientist, your alarm bells might be ringing. Tokenizers like byte pair encoding are notoriously bad at numbers. The string 512 might be one token, but 513 might be split into 2 separate tokens. How can the model possibly learn a smooth, continuous control space when the tokenization is so jagged? And you'd be right to be skeptical. In fact, this is exactly why the robotics community largely ignored this approach. But the authors of VLA-0 discovered that with 2 clever algorithmic tweaks, this setup doesn't just work, it actually beats the complex models. Here is the first hurdle. When you train a transformer on a sequence of numbers using standard teacher forcing, it gets lazy. It realizes that robotic actions are just smooth trajectories. So instead of looking at the camera image to figure out what to do, it just looks at the previous numbers in the string and extrapolates the curve. It becomes a simple Markov chain, completely ignoring the visual input. To fix this, the authors introduce a technique called masked action augmentation. During training, they randomly mask out characters in the target action string. Think about what this forces the network to do. Because the local autoregressive context is suddenly broken and filled with holes, the attention heads have no choice but to route information from the image embeddings and the language instructions to predict the missing values. It explicitly forces the model to ground its numerical text generation in the physical reality of the visual scene. The second piece of the puzzle happens during inference. Because raw text generation can still be slightly noisy, VLA-0 predicts a whole sequence of future actions at every single time step. Since the model operates continuously, you end up with multiple overlapping predictions for any given moment in time. VLA-0 simply ensembles these overlapping windows, taking the average. In the math of probability, this effectively marginalizes out the high-frequency tokenization noise, leaving behind a beautifully smooth, highly accurate physical action. When you put this all together, no new parameters, no vocabulary hacking, just smart prompting, masked training, and temporal ensembling, the results are staggering. On the Libero simulation benchmark, VLA-0 achieves a 94.7% success rate. It doesn't just outperform every other model trained on the same data. It actually outperforms massive models like Pi-0 and Molmo-Act that were pre-trained on gigantic, real-world robotic datasets. And it does this all while remaining incredibly lean. In real-world physical tests on an SO-100 robot arm manipulating blocks and apples, it outperformed small VLA by over 12.5%, running at a brisk 4 Hz inference speed. In machine learning, we often fall into the trap of thinking that complex problems require complex, highly engineered architectures. VLA-0 is a beautiful reminder of the bitter lesson. Sometimes the most elegant solution is to just trust the general-purpose architecture. By treating the physical world simply as a different dialect of text, we can let the native power of large language models do the heavy lifting. No special modifications, no new tokens, just numbers, text, and an unmodified brain learning to move. Thank you for watching.